Welcome to this video where we classify chemical reactions in a different way to the way we have done it before. So just to recap on how we classified chemical reactions in previous videos, we firstly looked at whether chemical reactions give out a net amount of energy or whether they take in a net amount of energy. So we call those reactions exothermic if they gave a net amount of heat or light or electrical energy out to the environment, or we refer to them as endothermic reactions when they took energy in from the environment in order to produce the products. Then we looked at whether reactions take place spontaneously or non-spontaneously. So if a chemical reaction took place without any extra energy needing to be supplied in order to activate or to start the chemical reaction. In other words, there's enough energy in the environment in order for the reaction to happen on its own. They were referred to as spontaneous chemical reactions. If extra energy needed to be added by means of, say, for instance, a flame from a match in order to set off a cracker, that would be a non-spontaneous reaction because the environment doesn't have enough energy. Sometimes we refer to ambient energy. Energy in the environment is ambient. If there's not enough ambient energy in the environment in order to provide the activation energy, then an extra amount of energy would need to be supplied. That would be referred to as a non-spontaneous reaction. Now, in this video, we are going to classify reactions as to whether they are synthesis reactions or decomposition reactions. And in doing so, we are going to look at a different aspect pertaining to the reactions. In other words, we're going to look at how complex the products are in comparison to the reactants. So let's start off by looking at synthesis reactions. Synthesis reactions are defined as processes, in other words, something changes from one state to another. They are processes where simpler reactant substances form into more complex product substances. So we can represent this in a general way very simply as follows. We can say if we have reactants A and B, then the process of the reaction is going to result in a product that has a more complex structure. So now let us consider the first example in this video.
This is a mixture of sulfur and iron, and it's kind of a dark yellow colour. Here is a magnet, so if we just test the sulfur we can see nothing happens. If we test the iron we can see that that is lovely and magnetic, and if we test the mixture we can see that the iron filings in there are dragging up the sulfur. So what we're going to do now is heat this mixture of iron and sulfur and see what happens to it. So I'm heating the mixture of iron and sulfur. You'll notice that I'm pointing it away so that any gases that come out of the top aren't directed towards anyone's face. And heating this quite strongly, oh, little pop of gas there. Heating this quite strongly, and hopefully soon we will start to see it changing colour. There's quite a lot in there. We can start to see it going black already. Starting to see it glow there. Quite a bright glow if I just tilt that, if you can see it, and that tells us that a reaction is taking place. So once it's glowing and you can see the vapour coming out the top, we can stop the experiments. So now the test tube has cooled down ever so slightly, what we're going to do is wrap it in newspaper, smash it with a hammer and see what happens. Lovely satisfying sound there. So this is what we have. We have this little lump in here which is attached to all of the glass.
So this example is referred to as the synthesis of iron sulfide. So the word equation would be iron plus sulfur. So the iron was the iron filings that are magnetic, and the sulfur was the yellow powder. So these two substances were the original reactants. And then after the chemical reaction took place, iron sulfide was formed. Now, referring back to the video, and the nice thing about having a video is you can actually pause and rewind and go and look at the reaction again. You will note that there was a lot of energy that was required to get the iron and the sulfur to actually react. And that energy from the Bunsen burner was the energy required, the energy in, or the activation energy, or the activated energy required to separate the atoms of iron from each other in the iron filings and the atoms of sulfur from each other within the sulfur powder, and get them into an excited state, which we call the activated complex. And then recall that once the reaction started to take place, there was a color change that started to take place. So that was one of the ways that one could observe that the reaction was starting. But once the sulfur and the iron atoms had reached their activation energy, or should I say the activated complex, then when giving out energy, note that the actual reaction mixture actually lit up. It started to glow, and you could actually see there was a color change in the flame on the outside. And the reason for that was that was where the energy was being given out by the reactants in forming the new substance iron sulfide. Now, iron sulfide has very different properties and a very different characteristics to the iron and the sulfur. Iron sulfide is exceptionally hard, and it's a very different substance, as could be seen in the final part of that video. So that is what a chemical reaction is. It's where it's not just changing a substance from one phase to another, like melting ice, for instance. It's an actual structural change on a molecular level, producing a completely different substance. So the chemical equation, or the symbol equation, would be Fe. S is for solid. This little bracket here is a phase symbol. Iron in a solid state plus sulfur in a solid state produces iron sulfide in a solid state. So representing it in a particle diagram, and obviously we're only representing one iron and one sulfur atom producing one iron sulfide molecule, but in practice it would be millions and quadrillions and quadrillions of iron atoms and sulfur atoms reacting together to produce zillions of these iron sulfide molecules. But we represent the reaction symbolically, or should I say in a particle diagram, very simply. We take one iron atom plus one sulfur atom is going to produce a more complex iron sulfide molecule. So because the product has a more complex structure than the reactants, this is a synthesis reaction. So now we get to our second example of a synthesis reaction, and this is where we take magnesium and react it with oxygen. So please take a look in this video.
One of the basic synthesis reactions is the reaction of a metal with a nonmetal to form an ionic compound. In the reaction that we're performing here, we're reacting magnesium metal with the oxygen in the air to produce magnesium oxide. The combustion reaction is a very rapid reaction, producing heat and light. What we're left with is a white solid, which is the magnesium oxide.
So the second example is referred to as the synthesis of magnesium oxide. The word equation would be magnesium plus oxygen gas produces magnesium oxide. The magnesium was in the form of a metal ribbon. The oxygen gas was invisible. It was in the air surrounding the magnesium ribbon. And then the magnesium oxide was the white powder that was left at the end of the reaction. So the chemical equation, or the symbol equation, would be MgS, magnesium solid. Two magnesium solid atoms will react with one oxygen molecule. Remember, oxygen is a diatomic substance. It's made up of molecules with two oxygen atoms. and it produces 2 magnesium oxide molecules. Now, these coefficients, these numbers, you do not need to worry about producing them on grade 8 level. There's a whole section in grade 9 where you will focus on what we call balancing chemical equations, and this is what balancing is. But for the time being, I can just tell you that it's based on the fact that atoms do not get created or destroyed. There's a conservation of atoms. So if you have 1 magnesium atom on this side, you can't produce 2 magnesium atoms on this side. So this diagram is actually wrong. So what we need to do here is we need to add another magnesium atom, because 2 magnesium atoms on the reactant side will be needed to produce the 2 magnesiums on the right-hand side, and likewise with the oxygen. So if we look in this chemical reaction, and we can say it's a chemical reaction because a completely new substance was produced. The magnesium was a metal, the oxygen was a gas, and the magnesium oxide was a solid. We see there 2 MgS, because the ribbon was a solid. The oxygen was a gas, so we got the bracket G for the gas phase. And the product was magnesium oxide, which was a solid powder. Now note that there was a huge amount of energy given out in the form of light and heat. And that energy was the equivalent of about half the temperature of the sun, about 3,000 degrees Celsius. That's why it burnt white. Burning white means it's burning at an exceptionally high temperature. So this reaction doesn't just happen on its own. The conversion of magnesium to oxygen either takes place over a very, very long time in the form of what we call rusting. But if you wanted to combust, burn quickly, you need to put a huge amount of energy in, which came in the form of the flame. But the energy that was given out, that was because the energy was given out because the magnesium and the oxygen atoms, when they were in an activated complex state, were at a very high energy, and they dropped down to a very low energy to produce the magnesium oxide power. So a lot of energy was given out to the environment. But let's look at it from a synthesis point of view. The reactants are made up of individual atoms, magnesium atoms, and oxygen molecules, which are combined together. During the process where the activated energy is supplied, the energy is taken in, these break apart. A lot of energy was required to separate the magnesium atoms from themselves within the magnesium ribbon, and energy was required to separate the oxygen atoms in the oxygen molecules apart to produce the activated complex. Energy was given out, and the final product was magnesium oxide molecules. Now, in strictest terms, they're not really molecules. They are what we call formula units, because they are what we call ionic substances and not molecular. But that's not for grade 8. In grade 8, we can think of them as molecules. You'll learn more about this in grade 10. So notice that these molecules are more complex than the original reactants. Yes, there was molecules here. This was oxygen, but it was 2 oxygen atoms. Whereas here, it's a magnesium and an oxygen. So this is more complex. This molecule is more complex than this molecule. So this is a synthesis reaction. The structure of the molecules produced, the structure of the product molecules, is more complex than the structure of the original reactants. Therefore, this is a synthesis reaction. Now, I would like to ask you a question. Let's go back to the previous 2 methods of classifying reactions. Remember, exothermic and endothermic, and spontaneous, non-spontaneous. If we think of the first reaction, the synthesis of iron sulfide from iron and sulfur, was it an exothermic reaction or an endothermic reaction? Was it spontaneous or non-spontaneous? Pause this video and think about it. Well, the answer is as follows. A large amount of energy was given out and observed when we observed the iron and sulfur reacting with the iron sulfide. Remember, it eventually glowed and there was a flame that was produced on the outside. That points to the fact that net energy was given out to the environment. So therefore it was an exothermic reaction. Was it spontaneous or non-spontaneous? Definitely non-spontaneous, because the iron and the sulfur weren't just going to react together to form iron sulfide. They needed to be heated up. Energy needed to be supplied in the form of the Bunsen burner flame in order for them to actually start reacting. So the first reaction was a synthesis reaction. It was exothermic and it was non-spontaneous. Let's consider the second one. The magnesium and the oxygen reacting to produce magnesium oxide. Was it exothermic or endothermic? Was it spontaneous or non-spontaneous? Pause the video and think about it. Well, think of the amount of energy that was given out. It was a huge amount of energy, so it was obviously exothermic. It was actually more exothermic than the first reaction, which was the synthesis of iron sulfide. So this was a hugely exothermic reaction. It also was not a spontaneous reaction. This did not happen on its own. The magnesium needed to be heated and the oxygen needed to be heated with a flame in order for the reaction to start. Obviously, once the reaction started, there was a huge amount of energy given out. But to initiate it, the flame needed to be supplied. So therefore, it was non-spontaneous. So both reactions with synthesis reactions, they were exothermic and they were non-spontaneous. And this is often the case with synthesis reactions, that they are exothermic, most of them are exothermic, and most of them are non-spontaneous. But there are synthesis reactions which are spontaneous, like for instance the rusting of iron. When iron combines with oxygen over a very long period of time, like for instance when an iron nail rusts over a long period of time, the iron and the oxygen join to form iron oxide, which is a form of rust. The same is true, for instance, with magnesium. If you left magnesium for a very, very long time, eventually the oxygen would react with magnesium and produce like a grayish rust layer on it. But that would take very long. So, we have now come to the end of this video on synthesis reactions. So, what is a synthesis reaction? It's a reaction which produces a product which has a more complex structure than what the initial reactants had. In the next video, we are going to look at a different type of reaction, namely decomposition reactions.